today I'm going to talk to you about LTTng and how we can use it to solve complex problems in production. So the topics we cover are tracing, the different kinds of tracing, because usually there is a mix between terminology between trace buffering, aggregation, sampling. Then we talk about what is LTTng and why we want to use it for this kind of use cases. And then we discuss the four main modes of LTTng and how to configure them and why they are useful for various use cases. So my name is Philippe. I'm a software developer at FOSDEM. We develop and support LTTng. So I work on LTTng, kernel and space tracer, and barrel trace, the text converting software. And also the author and maintainer of the latency tracker and LTTng analysis project. We'll talk about that during the presentation. So the first kind of tracer that I want to talk about is trace buffering. So that's usually what we refer to as tracing. It's just fast and efficient logger. So you take the instrumented code and it generates logs. But the difference between normal logging and tracing is that it generates usually a huge amount of trace, and that's why we use buffering, because we want to extract as much information as possible and make sure it's complete and you have the full idea of what's happening on your system. So it's usually really application specific. It's meant for developers and it's created by the developers, so it's really just for debugging your code usually. So the common tracing tools in Linux are trace, which is in the kernel. Perf can be used as trace buffering also, but it's not the main mode. And of course, for the LTTng. So the buffering use cases is to understand complex problems. So you need as much information because you want the low-level data and then be able to process the trace offline, just read the data and see what was happening. So it can be used to solve concurrency issues, race conditions, or drivers issue, low-level problems. You also have hardware tracing, which does this kind of trace buffer. So it's usually considered the last line of defense because when you are at the end of using a tracer, that's because you didn't find a solution with a simpler tool before. So that's usually why it's not that popular to use a tracer and why you always have to rediscover how it works, because usually you don't use that every day. But with what I'm going to show you today, you will see that it can be used in production for cloud and monitoring use cases. The second type of tracing is trace aggregation. So if you have heard about T-trace, that's what they did. So it's the same source of information. It's usually trace points in the kernel or dynamic source. But instead of logging the data, you aggregate them, you extract parameters, and then you output reports. So it can be averages, mean, max. It can be also used to just give a profile of I/O or the kind of I/O operation for a specific file. So it can be really configured to make sure you understand one system, but it's at runtime. So when you unload the probe or the program, you get the report, and that's it. You cannot go back to time and see what was happening. You just have this source of data. So it's just aggregation. So the common tracing tool, aggregation tools on Linux are systemtab. Now we have eBPF, which can be which you can use in BCC, which helps creating user space program that load eBPF code, and latency tracker, which is a tool that we work on. We talk about big data. And the third kind of tracing tool I want to talk about is sampling or profiling. So it just takes the current activity of the system at a very typical time. So it can be time-based, or it can be when the counter overflows. So you could have sample every 1,000 instructions, just what's happening on the system at the moment the counter overflows. And it's used to extract statistics, but mainly on stuff. So if you have just per stuff, you want to see exactly what was running on the system, and usually you have to find what was the activity and why, where your code was happening at that moment. So for LTTng, the main part is that it's a fast command tracer, as fast as ftrace. The main difference is that LTTng also extracts the payload of the system calls. Ftrace also just outputs the value of the parameters, but if you have pointers in there, it doesn't dereference them. So LTTng does that. It's also a fast user space tracer. It doesn't rely on system calls for each trace point. So compared to tracing or logging, where you would have at least one write system call every time you want to output the line. In LTTng is in memory, and when the buffers are full, we extract them on this. And it's designed to run in production environment. So it's not just a debugging tool when you don't have any more choice. You can use that all the time. And it's filled with a lot of tools for post-processing traces and batch or graphical. We will see some examples later. So LTTng can generate a lot of events. If you configure a default system with kernel tracing on this laptop that does nothing, you can generate about 54,000 events per second. And if you run the same configuration on the server that's busy, you generate 2.7 million events per second. So it's 95 megabytes of trace per second. So that's a lot of lines, and you have to process them after. So the default mode is maybe not for everyone, and we will see why we have the other modes and why they are useful. So the first mode, like I said, is the default. It's just extract the trace buffers and write them on disk or on the network. So you can have a LTTng relay that just waits for data packets to come. So if you don't have space on your local system, you can send the trace remotely. So you are only limited by disk space and your willingness to process big traces. But the main use case is that you want as much information as possible. You don't know what you are looking for. You want to get just a big picture of what the system is doing, and maybe sometimes you just don't know when the problem happens, so you want to record everything and then do the post-processing. So, and it's also used continuous integration systems, Jenkins, where you can just record the trace while the tests are running, and then you can post-process if something weird happens. So to create a disk or streaming session, you just create the session, enable events, start the session, you wait for the activity or the problem to happen, then you stop the session, and then you can process the trace. So you cannot process the trace while it's running, because you really have to stop before being able to access the data. So it can take some time. If you take a real-world example of disk and streaming mode, we have the full write-up of this case on the link at the end. But basically, it's a use case where users complain that the website is slow. You don't know why, you don't know when, just sometimes they complain. And the standard monitoring tools usually don't record this kind of activity. They will just take a sample every minute of how many packets per second or even what's the average latency. But usually you don't see micro spikes in the monitoring tool. And that's where this kind of observation tool comes really handy. Because now what we do is that we record every I/O operation, scheduling, and all activity of the web server. So we can specify only a process. And when somebody reports a problem, then you can go to the tool, run some post-processing tools, and extract really detailed information. So that's just an example. It's not meant to be really readable right now. But just to give you an idea, here it's the I/O latency stuff. So it takes the trace and extract the top four for the open, read, write, and sync kind of operations. And these two I shown here, and the first one is the open of the PHP file, session file. So that's the web server that's trying to create the new session on the disk. And it took around 500 milliseconds to open this file. And if we look at the bottom, we also see that there is a sync that's happening on the system at the same time. So it's working the disk and the Apache server cannot create a session file, so it's just hanging. So that's the kind of micro spike that we wouldn't see with usual monitoring tools. But that's possible. And after that, if you look at the blog post, if you want more details, we dig really deep into how we found this and how to explain where the sync comes from. The second one I want to talk about is the live mode. So it's basically the same process. You create a session, but the main difference is that you attach to the session. So you can process the trace while it's still running. So that's a big difference, because the other case you have to stop the trace and then process it. In live, you can attach to it and start processing the data. Another difference that you can use that normal model tool is that the trace file size and trace file count. So you can record. See, if you don't want to keep the full history on disk, you can limit the disk space that's used by the trace. So you attach to the session, you can process it, but it's still writing to disk, but at least you have a bounded disk usage. Live mode in itself is useful for low throughput logging because you don't want to read 54,000 events per second on the console. So if you configure really specific events that are really low throughput, maybe you want to attach to a live session and see the events when they happen. But it's also used for distributed and embedded system or monitoring out of them. So you send the trace to a relay and then you do your analysis on the relay. So you don't have too much impact on the system that is being traced. You just use it to trace, send packets, and then out of them you have a system that's processing it. So the big difference between the first mode and this one is that you have the dash live on the create operation, and that you can use LTTng to view while the trace is running, instead of having to stop and then do. And of course you can send also the trace to a remote server. For the bounded disk usage, you can configure your channels to be only, for in this example, 4 files of 10 megabytes. So it will rotate on those 4 files for each CPU on this channel, and that way you have 40 megabytes per CPU at most of disk usage. And of history also, of course, so you have to see how you want to process it. The third mode, one of the most interesting, is the snapshot mode. So instead of having the traces full buffers in memory, then we extract the data, write it to disk. In this mode, we don't write to disk by default. So we just trace the memory buffer, and that's it. It's just writing events, and when the other events, when new events want to come and the buffers are full, we just override other events. So it's low overhead because instead of doing I/O, we just write memory. And when you want to extract the trace, you just type FOSDEM snapshot record. It takes the content of the buffers in memory and write them to this. And then you can do your post-processing. So you can configure triggers in your applications or any kind of monitoring tool to just, when you detect something, just record the snapshot and you get a backlog of maybe a few seconds before the incident happens. So you can use that. We have the helper to configure the core file handler. So when you generate the core dump, you can also trigger FOSDEM snapshot record, and then you get the full activity right before the segmentation happens. Of course, since we are writing in memory and overwriting the data, the time span inside the snapshot depends on how much memory you want to dedicate to the tracing session. But that's really something that you can configure, and depending on your event rates and size, you will have big or small snapshot at the end. So the use cases are fault-based applications. When you know when the high latency is detected, you can trigger the snapshot. You can also use it as profiling tool, because you can say every 5 minutes I want to see a history of the last few seconds and just see what was happening on the system. Of course, continuous integration also can be used, because when the worker detects an error, you can just record the snapshot, and at the end you will be able to process the crash and why it happened. The difference between the default mode and the snapshot mode is that on the creation you specify that snapshot, and that's it. So that you just create a session and you order and start the session, and when you want, just type FOSDEM snapshot record. It doesn't push the data from memory, so if you just type FOSDEM snapshot record twice, you just get approximately the same snapshot, maybe just a few microseconds later. So if you want a concrete example, here we are monitoring the website with the latency tracker, with just an aggregation tool that uses trace points and just computes the time to first byte between the receive or request to the first actual send of data. And we just track the latency of this operation. And from the graphs, we see some time with spike. So that's fully automated at this point, compared to the first use case where we had to wait for users to report. In this case, it can be fully automated with aggregation tool. So we detect spikes, and now with the snapshot mode, we can extract the snapshot every time the spike is detected, and then run post-processing on just a small trace. I think we have 1 second of storage, just before 1 second before the high latency happened. So we can see the data. So if we look, that's meant to be reliable again, but just to give you an idea, it's in Grafana, we have metrics plotted for each latency measured by the latency tracker. And every time you see a bigger line that's above the baseline, we also have an annotation with a small orange triangle. And if you click on this orange triangle, you get reports that are fully automated in the end. So the latency tracker detects high latency, extracts the snapshots, sends it to a server. The server processes the trace to extract the profile. Here it's I/O latency frequency distribution, and then it's annotated to the Grafana monitoring. So you just click on the link and you can get a full picture of what was happening exactly at that time. So here in the latency frequency, 2 outliers in the range of 4 microseconds compared to everything that's in the range of 5 microseconds. So, and then we have tools to dig into the time periods. So I'll let you look at the documentation if you want. And finally, the last mode that we have been working on for the past 8 months, it's the rotation mode. So it's expected to be released in March 2018. It's currently under review. And the idea of the rotation mode is that it combines the normal tracing mode, which is just outputting a trace on disk, with the snapshot mode, which is creating small traces. So now we write to disk all the time, and whenever we want, we can just type LTTng rotate, and it takes the current chunk of data and write it into a separate folder, and the trace continues to write on disk. So in the end, you could configure a trigger that every minute executes LTTng rotate, and you would have self-contained 1 minute tracing instead of having a huge trace that covers the whole tracing session or small snapshots. So it's in between, and again, it's dependent on the use case. Sometimes snapshots are better for the other use cases, but this is really useful. Also, you can use it to compress the trace. We have customers that trace all the time, and traces become really huge. So they want to, every hour, just rotate the trace, compress it, and keep it for storage. So if they need some time to use the trace, you can just get from the storage and process it, instead of having to stop the session and then you can lose events in between sessions. With this mode, you don't lose any events, just switching the directory, and you can use the trace as a really small self-contained trace. So it can run indefinitely depending on the disk size. But if you can also just rotate, process the trace, generate reports like that, and then discard the trace, you don't keep too much storage on the disk. So the use cases are continuous monitoring, because you can use that to every minute extract really low level data. You could use filters to see you just want some I/O metrics from Apache. That it's more basic because you choose around the case. And also for post-processing, because sometimes just generating this graph from a 10-second trace can take more than 10 seconds, depending on the load and the number of events. So with this kind of process, you can just extract the snapshot, send it to a worker that will do the post-processing of the trace and continue working on the server. And then, so creating a trace is basically just like creating a disk session, just create more. And after the start, when the activity is is running, then you can just type stng rotate, and it gives you the path of what was the data between the start and the rotate. Then if you wait a bit and re-execute rotate, you will get the path with the activity between the now and the previous rotation. So you will really get the full picture of what was happening on the system between the two rotates. And then we have proof, we have a trace compass, which is a graphical proof. You want to look at the data graphically and see that means we can read around the discussion on the predictor, but it gives you a way to explore by process or by results or CPU interrupts. Through this, you have the histogram, or kind of graphical view. And we are also working on the new tool, LTTng scope, which is also a post-processing tool to be able to really look into a trace and find what you are interested in. Those are especially useful for race conditions. You don't want statistics like with the tools I presented before. You really want to see the full timeline at the nanosecond scale and really see what was happening, what was currently running on the system, why this process got preempted. Maybe you will see interrupts that are preventing a process from running. You will see everything from there. So it's really low-level group, and we want smaller traces because that can take ages to process this kind of snapshots or rotations are really good for this kind of thing. So in conclusion, FOSDEM allows to extract low-level high-volume information from production environments. It's efficient camera user space traces. The two traces are already separate, but at the end you can merge them and see the camera events in respect to the user space, and you will see the full time. It can be used for monitoring and fault investigation. We know a few companies that use it in telecommunication and automotive environments also. And there are multiple ways to configure LTTng. And depending on your use case, you can just select the one that's most interesting for you. So, if you have any questions.
You mentioned at the beginning that there are agents for Java.
Yeah.
So, I'm mostly a PC user, so I don't know much about LTTng. But what kind of things these agents provide, say USDT and eProbes and things like that,
No, it's not for USDT programs. It's really just agents that run inside the Java or Python languages. So they are built in Java, but they come to LTTng with, or they allow you to process output user space traces from user space. So instead of USDT or UPro, where you have to switch the camera every time, it's just fully user space tracing.
Okay, and I'm also curious, where do you see, again, as someone who's taking most of that is going to be, not for any particular reason, but as opposed to just where do you see its strengths and weaknesses compared to, say, like F-Trace or
LTTng and
mostly PCs? I'm curious.
Okay. So the main difference I looked at the beginning is that you have trace buffering and trace aggregation, and those are really complementary. With ECC and EPF, you get statistics, you get errors, you get reports when something really interesting happens. With LTTng, you get the full backlog of what was happening at the time on the system. So you can go back in time and look at the detailed trace. Compared to ECC or EPF, you would just get histograms or statistics. So usually we use trace aggregation to take problems, and then if we want to go back at that exact time when the high latency happens, for example, you look at the trace. So that's why
you can do this with PCC as well?
yes, but it's not meant for buffering tool. You can use the perf method, but it's really not meant for high throughput, just as a trace or XP. So it's just a matter of because we can extract a lot from it, but it's that it's not meant for continuous living.
Any other questions?